Hello everyone, Professor Dustin here, and this video is going to be a solution to this problem, which was called junk probe collision. So in it, we have a collision between a spaceship, which kind of looks like Voyager, and an asteroid, which kind of looks like a face. The probe has a mass and a speed traveling directly along what we could call the x direction. In fact, let's put the axes on there. So if these are the axes we're going to use, x, y, then the probe is traveling directly along the x direction. The asteroid, which has a mass, the space junk has a speed of 150 meters per second, and it's going along the y direction only. They collide perpendicularly, so that's why I know that I could put that that coordinate system right there at the right angle. After the collision, they stick together, and the path of the probe has been deflected by 10 degrees. So this angle right there is 10 degrees, and you can see that they are stuck together now. So there's two parts to this. What is the mass of the space junk that hit the probe, and how fast are the probe and the space junk moving now after the collision? First thing we should recognize is that's two independent questions, but in these kinds of problems, it doesn't necessarily mean that we should definitely solve A first. It might be better to solve B first. I'm not saying that's the way I'm going to take. I'm just going to start doing the problem and sort of decide on the way, but we might find it more beneficial to find how fast the probe is moving first and then find the mass of the space junk. So how are we going to solve this? Well, it's a collision, so it's going to be some kind of conservation of momentum and conservation of energy type problem. They are colliding and sticking together, so though it's not said specifically in the problem, this is definitely an inelastic collision. Most collisions are inelastic, and specifically collisions that have objects that stick together are definitely inelastic collisions. So this is a case where we're going to use conservation of momentum, delta P equals 0. That means that there are two separate equations, conservation of momentum in the x direction and conservation of momentum in the y direction. So the way I like to do these kind of problems is split up very carefully what stuff is happening in the initial and what stuff is happening in the final. I want to split this up into x and y directions, not into one object versus another. So I'm going to be calculating the initial momentum in the x direction and the initial momentum in the y direction. Now there could be two objects, right? There are two objects, so in the x direction there could be two pieces, like P probe in the x direction initially, P space junk in the x direction initially, but the probe is the only thing that's moving in the x direction. So this is going to be mass of the probe, velocity of the probe, and let me go back over here and label these carefully. That is MP, that is VP, this speed, that is going to be the velocity of the space junk, and then we have to realize that we don't know what the mass of the space junk is. We don't know how fast the probe is moving. Final is question mark, and actually let me label that the angle is theta. Okay, so now let's go back over here. I can now enter the momentum, the initial momentum in the y direction. It's only due to the space junk because the spaceship is only moving in the x direction. So mass of the junk times velocity of the junk. And let's just be totally clear that this is our unknown, right? One of our unknowns is the mass of the space junk. So same splitting in the final state. We want the momentum final in the x direction, momentum final in the y direction. So the two objects are stuck together, so we're going to have mass of the probe plus mass of the junk times the velocity final in the x direction, and then we'll do mass of the probe plus the mass of the space junk, velocity final in the y direction. So if you remember from class, I frequently advocated for writing these guys as components first and then deciding if you needed to rewrite them, because indeed, if I draw those onto my picture, there's the velocity final in the x direction. There's the velocity final in the y direction. But if I label the magnitude of the velocity vf, you can actually write these velocities vf as cosine vf cosine theta, and the y direction as vf sine theta. So you can pick either representation. You can either represent them as components. So now, before deciding which representation I want to use, the component representation or the magnitude direction representation, let me continue by putting them into the conservation of momentum equations, because that's really going to show us how hard the job is that we have. So conservation of momentum in the x direction, pxf minus pxi is 0. Pxf is just going to be the sum of the masses, mp plus mj. times the velocity component in the x direction, subtracted off by the initial, which is mpvp. Doing the same thing in the y direction, the change in y is 0. That means that pyf minus pyi is 0. And again, we get that for the final momentum, that's the sum of the masses times the velocity now in the y direction, subtracted out by just the asteroid piece, or the space junk piece, rather, mj vj. Okay, so now let's look and decide if we can actually solve this system of equations. We have two equations, but the problem is that it appears that we have three unknowns. Mj is an unknown. It shows up in three places. But Vfx and Vfy are both unknown. We actually don't know what those two things are. Now, we could solve this by going back up here and changing the representation, right? Because if we replace Vfy with Vf sine theta and Vfx with Vs cosine theta, we know what theta is. So we're replacing two unknowns with one unknown. So that would make this two equations, two unknowns, and it would indeed be solvable. But if we make one more additional observation, we can make this problem actually very, very simple. We have, well, not very simple, but a little simpler. So we have a nice triangle up here that has some stuff in it we know and some stuff we don't know, but specifically it has our two unknown sides, Vfx and Vfy, and a known theta. These are related to each other by trig functions. Specifically, they're related by the tangent function. So tangent is opposite over adjacent. That's going to be Vfy over Vfx. So the way that this helps us is that we can now solve for Vfy from this expression, solve it right there. That means that this equation will then have only one unknown because I'll replace it in there. I'll do the same thing with this equation, solve for Vfx, put it in there. But now this equation will have only one unknown as well, mj. So we'll have a left-hand side, which we know, tangent of 10 degrees, a right-hand side, which is some algebraic function that includes just one unknown that we can then solve for. So this is going to be the quickest way to get to our solution. So I'm going to use this. Of course, first I have to solve for Vfy and Vfx, so let me do that real quick here. So that's mj vj divided by mp plus mj, and notice what I did is I simply took this piece, brought it to the other side, and then divided by the total mass. Do the same thing up here, bring this to the other side, and then divide by the total mass. And that gets me a very similar expression, just with slightly different variables, mp, vp on top, and need a little bit more space. But now what I should do is just plug these two things directly into here, and then we'll see that we can get the mass out pretty easily. So I'm just going to rewrite the tangent. Put in Vfy. Vfy is mj vj divided by mp plus mj. And then Vfx is mp vp divided by mp plus mj. Got a very nice cancellation because the total mass is on the bottom of the top and the bottom equation. So we end up with just a ratio between mj vj and mp vp, which now we can just solve for the mass of the space junk, which is going to be mp vp over vj times the tangent of the angle theta. If we plug that into our calculator, we'll get that the mass is 5.88 kilograms. You know, and intuitively that might make a fair amount of sense. This is a spacecraft which is 100 kilograms getting hit by something which is relatively small. The deflection angle is relatively small. Also, this thing is moving very fast. I don't think we can, assign too much more reality to that, but certainly a relatively small mass makes some sense. That's the answer for part A. To get the answer for part B, we want to find out what the velocity is, so we're going to have to go back and do something else. Because when we do it this way, when I use this tangent trick, normally when you find a solution to one unknown, you can take that unknown and plug it into some very, very simple expression to get the other one. We can't really do that in this case because I use this kind of trick to get the answer. So I do need to find a velocity, a way of stating the Vf. Since I use geometry to find this expression, maybe there's a nice way of using geometry to get the answer for the final velocity. Indeed, that seems to be true because you can get the final velocity Vf by using the Pythagorean theorem now that we actually have an answer for Vfx and Vfy. So we could actually put numbers on Vfx and Vfy to figure out what the actual components are, because now everything in these two expressions are completely known, and then we would use the Pythagorean theorem. like that. Now, I guess I'm not going to go through and actually find out these individual components. I'm just going to plug these two expressions into the formula up there. So that looks like that. I can simplify that a little bit. Notice there's an MP plus MJ squared on the bottom of both terms. I could take that out and also take the square root of that to get the following thing. I'm not saying that's like an enormously amount less complicated, but in any case, we have all the numbers, so it's just plugging things into your calculator. And the final speed you get is like 48 meters per second. I did see that in class a few people were getting like 47.9. That's probably more accurate. I might have done some rounding when I did this problem originally, I'm not sure. But so anyway, there are the two answers here. 5.88 is the mass and 48 meters per second is the speed. The generic way that you solve these problems is what I followed until getting to this step where I had this like sort of many unknowns. It so happens that when you're looking for something like the mass, it's a little bit easier to remember these kind of trig identities. But again, if you had gone through and just done this replacement was definitely required for this problem. You can't get away by not doing it. But if you do it, and you do it here, then just try to straight solve for the mass. I saw a couple people doing that. It's a little bit lengthy, but it's totally doable, right? This is just a slight shortcut that makes things a little bit simpler by looking at the geometry. So you want to be aware of those, but you also should just be ready to do a bunch of algebra to get the answers to these problems, because often they require a bunch of algebra. Okay, great. So this has been a solution to the space junk problem. I hope it has been helpful. Thanks for watching, and I will see you next time.